Dear students, welcome to my YouTube channel PCM Academy. Today we will discuss about Heisenberg's uncertainty principle. Actually, we are in a lecture series for quantum mechanics for various competitive exams, something like IIT JAM, JEST, neet, this kinds of exam. So if you are BSc Honors student or MSc student, then this channel will be very helpful to you. And if you see more videos, then you can go to the playlist. You can see some playlists are also created, and which course is suitable for you, you can see. Okay. So today we'll discuss about Heisenberg's uncertainty principle. In the last class, I have discussed something about the particle versus wave and the dual nature. Okay, when we will see the particle behavior of a quantum particle, something like electron, and how we have seen the wave behavior. Okay, so we have discussed in great detail. So in the last class, so you can see this class. You can go to the playlist of quantum mechanics and you can see all the videos that I have discussed on quantum mechanics. Okay, I have discussed some videos on mathematical physics also, so you can go to the playlist and you can see. So now today I will discuss about basically Heisenberg's uncertainty principle. So what actually Heisenberg's uncertainty principle say? This is actually, it says that the indeterministic nature of the microphysical world. So whenever we have studied in classical mechanics, we have seen the macroscopic world, and in macroscopic world everything is deterministic. And the measurement, we can measure the position, velocity, these kinds of physical attributes we can measure to arbitrary level of accuracy. But in quantum mechanics, basically for the quantum particle, something like electron, which are very low inertia, we cannot predict their initial position, initial momentum, etc., this kinds of thing. So these are completely indeterministic. So here in Heisenberg's uncertainty principle, basically Heisenberg says the indeterministic nature of the microphysical world. Okay, so let me tell you something first before discussing the uncertainty principle. Let me tell you something about the classical mechanics or the classical system and the quantum system. What is the difference, basic difference between the classical system and the quantum system? So if you talk about classical mechanics or a classical system, that is in macroscopic world. So if you talk about classical system, then what is your approach? So what we actually have done in classical mechanics or in classical system? So we have a particle, something like this. So if you know the forces acting on the particle, then we can apply Newton's second law for this particle. And after solving the Newton's second law, we can predict the future position and the future momentum or the future path of the particle. So this is completely the deterministic. You know the Newton's second law, which is the second order differential equation, something like force is equal to mass time acceleration for constant mass, obviously, d2r upon dt2. So this is the Newton's second law. This is the second order differential equation. So if you know this force, then you can set a differential equation, and if you solve this differential equation, you will get two constant. Obviously this is the second order differential equation, so you will get two constant. So you have to find out these two constants also from the initial boundary condition. And what are the initial boundary conditions are? The initial position and the initial velocity, or you can say the initial momentum, because mass is constant. So if you know the velocity, you can easily find out momentum. So initial position and the initial velocity, that is at t is equal to 0, what is the position and what is the velocity of the particle, if you know, and if you know the forces acting on the system, then you can easily find out at any later time what is the position, what is the velocity, what is the acceleration of the particle, and you can also predict the trajectory of the motion. So this is completely deterministic, and you can determine position, velocity at any time to an arbitrary level of accuracy. But what is happening in quantum system? If you talk about quantum system, then what is happening over here? In quantum system, you cannot predict its actual state, its actual position and velocity, initial position and velocity, or any time you cannot predict initial position and velocity. You cannot predict its physical attributes as we have predicted in classical system, the classical attributes, the dynamical variable. But here we cannot find. So here the quantum mechanics is completely indeterministic. Here exactness has no meaning actually in quantum mechanics, because you know we have discussed in the last class that electron behaves something like sometimes like particle, sometimes like wave. We have seen in double slit experiment that if you open one slit, then the electrons behave completely like particle, and if you open two slits, then it will behave like wave. But we cannot see the electron from which slit it will pass. We cannot see its actual state, that from which slit the electron will pass, the electron is passing. For that case, we have discussed in the last class, there is also little bit of arise this thing, that is the inexactness, or you can say the indeterministic thing. And you probably know about the Davison-Garmer experiment also, that I have also discussed in the last class, that in Davison-Garmer experiment there also the electron behaves like wave. But if you talk about the Compton effect, the scattering of electron, so their electron completely behave like particle. But if you talk about classical system, in classical system, when that is particle, so it will always behave like particle, and when it is wave, it is always behave like wave. So in classical system, the wave and particle are mutually exclusive thing. But in quantum system, the particle behavior and the wave behavior of a particular system or of a particular particle is the two sides of same coin. So you have both. Maybe you can see only the one side, that is either particle or wave, but it is the two sides of same coin. So there exists particle behavior and there exists quantum behavior. So we cannot predict their state. It is always, if you talk about the wave, so you cannot talk it about it's localized. As particle is localized at a particular point, but it is not localized, delocalized, it is spreads. So you cannot find the exact position. So what we have to do, we have to find the different kind of mechanics. We have to substitute, obviously, the Newton's law in the form of Schrodinger equation, that will tell you later on. But in quantum system, what we have initially done, instead of position, we have defined the state of the system by using the wave function psi, that is psi arithmetic, you can say. So this is the state of the system we have defined for matter wave. Instead of particle, we have used matter wave, and the matter wave is characterized by this wave function psi. So the inexactness arises here. You cannot predict position and momentum simultaneously. So and keep in mind, quantum mechanics does not limit the measurement in accuracy of position or momentum. So if you separately measure position and momentum, there is no problem. But you cannot measure position and momentum simultaneously to the arbitrary level of accuracy. If you measure position to the arbitrary level of accuracy, then you have to compromise with momentum. And if you want to measure momentum to a arbitrary level of accuracy, then you have to compromise on position. So these are actually canonical conjugate variables, and these kinds of canonical conjugates variable, for these kinds of canonical conjugates variables, there is some uncertainty, and that is Heisenberg's uncertainty principle. And before going to state the principle, let me tell you one thing again, why these kinds of inexactness, or why these kinds of indeterministic things is going to happen. So what is the difference again in classical mechanics? If you talk about a classical particle, something like sand particle, okay, so if you talk about a sand particle or something like this, so this is suppose a sand particle, this is a classical particle. So if you want to find out its initial position and momentum, suppose it's have momentum, so if you want to find out initial position and momentum, what you have to do, you have to interact with light, you have to interact with photon, that means you have to interact with light. So when you want to find out, you want to see this sand particle, you have to interact with light, and the momentum of light is so little with respect to this sand particle. So it's so small, this momentum. So in comparison of sand particle, so it cannot deviate the path of the sand particle. It cannot change the state of the sand particle. So we have the exactness. We can exactly find out its state. But in case of electron, if you talk about electron, if you want to find out the position and momentum of electron, so and if you an electron has very low inertia, it has mass 10 to the power minus 31 kg, and if you talk about sand particle, it has mass some milligram maybe. So if you talk about here for this electron, and if you interact this electron with photon, then photon is bound to change the state of electron, because electron has very low inertia and photon had that amount of momentum, and that is sufficient to change the state of the electron. So whenever you want to interact with this electron with photon, it will automatically change its states. So you cannot find its actual state, its initial position and momentum. So you cannot use the Newtonian mechanics, and that's why the exactness and the deterministic thing is completely collapsed here in quantum mechanics. So what this Heisenberg uncertainty principle saying in this respect, that for any two canonical conjugate variable, so let us take an example, that is for position, the uncertainty in position, that is delta x, and the uncertainty in momentum, that is delta px. X with px, y with py, these are canonical conjugate variable. So the uncertainty, if there is a position uncertainty is delta x, and the momentum uncertainty, measurement of moment uncertainty is delta px, then this product will always be greater than or equal to h cross 1 2. And this is not a error of an instrument. This is actually the inherent property of nature. You cannot minimize the error less than this. So if you measure a position of a quantum particle, then you cannot measure the position more than the accuracy delta x equal to h cross upon 2 into delta px. So if you measure a position for a particular state, then in that measurement of position you must have these kinds of uncertainty delta x. So if you want to decrease the uncertainty in momentum, then obviously the measurement of uncertainty in position will automatically increases. So you can minimize the error in one, then you have to pay the cost on the other. That is the complementary principle, that is the Heisenberg, that is the uncertainty principle. Okay, and this is not for only x and px, this is also true for del y into del py is also greater than or equal to h cross by 2, and you can say del z into del pz, this is also greater than or equal to h cross by 2. And not only this, any canonical conjugate variable, something like energy and time, so that will be delta E into delta T is also greater than or equal to h cross by 2. And what this actually means, this means that if you measure the energy of a system within a time interval delta T, if you measure first E1 at a time T1 and another time if you measure E2, then the difference of these two measurement, that is the error in measurement. So for the same system, if you measure energy one times as E1, the other time as E2, and these are not same, these are difference, and the difference is delta E. So if you measure two energy at a time interval delta T, then you must have the uncertainty measurement is equal to h cross upon 2 delta T. This is the meaning of this. So this is actually the statement of Heisenberg's uncertainty principle. You cannot measure this thing, any canonical conjugate, simultaneously any canonical conjugate to an arbitrary level of accuracy. But if you measure separately one, then you can measure. So if you want to measure separately, suppose delta x. So if you have delta px, if you have delta x tends to 0, what this means? This means actually your position uncertainty is 0. In that case, your momentum uncertainty will be infinite. So this is the main concept of Heisenberg's uncertainty principle. And what you can do maximum, you can this interaction of light. So how you can minimize this uncertainty. This uncertainty is always greater than or equal to h cross by 2 pi 2, that is h by 4 pi. h cross means h by 2y. So you can minimize this up to delta x into delta px equal to h cross by 2, but that will be the minimum uncertainty. You cannot remove that uncertainty. You cannot remove the uncertainty less than this. So you always have the measurement, the uncertainty measurement, the product of uncertainty measurement delta x and delta px is greater than h cross by 2. So when it will be equal, it will be equal if you just interact with the particle with one photon only. So if you minimize the intensity of photon, because the uncertainty is happening with the interaction of light. Whenever you want to see the state, whenever you want to detect the state, in that case you have to interact with the light, and whenever you want to interact with light, its state is changing. So if you want to change its state, minimize, if you want to make this changes of state minimize, then what you have to do, you have to interact with light with very less intensity. So you have to just throw one photon, though this is practically impossible, but in ideal case, if you assume that you interacting with the system with one photon only, then also you will get uncertainty that will be h cross by 2. So this is the inherent nature of the system, the inherent property of the nature, you can say. Okay, so this is all about the Heisenberg's uncertainty principle. Now what we want to tell you about proof of this, an example of this. So there is the electron microscope. So if you want to find out one electron only, then what will be happening? Let me see. So suppose there is an electron and you want to interact this electron with one photon, Now what we have an electron microscope, suppose something like this. So suppose this is objective lens. Okay, the objective lens, here is an eyepiece. So suppose this is an electron microscope. So here is an electron, okay, and the photon is interacting with this. Now let us suppose that after interacting with this electron, the photon is scattered along this direction. Now if this half angle is theta, so this is your eye lens, the objective lens. This is your objective lens and this is your eye lens. Okay, now let us suppose that after interacting with this electron, the photon is scattering either in direction or in direction or in this direction. So now this is the maximum angle, scattering angle. Otherwise, if the angle is more than this, then it will not within this objective lens, it will outside the objective lens, so it will not reach the eye. Now what will happen? Suppose from here it will be something like this. Okay, then it will reach to eye, suppose. Okay, so this is the eye lens and this is the objective lens. Now what will be happening over here? Suppose this is your x-axis. Let us take this is your x-axis. Okay, now if the momentum of this scattered photon is p, suppose momentum is p, then you can see along this direction this will be p sin theta, and along this direction that will be p cos theta. So if the photon is scattered along this direction, then its momentum will be p sin theta, and if it is scattered along this direction, the momentum will be minus p sin theta. So the momentum of photon will vary from minus p sin theta to plus p sin theta. You can see it will vary from minus p sin theta to plus p sin theta. And as initial momentum along x-axis is 0, so obviously the total momentum of photon and electron must be 0 after collision, because before collision the total momentum was 0, the momentum of electron and the momentum of photon was 0. So after collision, the momentum of photon, you can say the momentum of photon plus the momentum of electron will also be 0. So what will be the momentum of electron? Will be minus of momentum of photon. So if momentum of photon is varying from minus p sin theta to plus p sin theta, then the momentum of electron will vary from plus p sin theta to minus p sin theta to minus p sin theta. So what will be the measurement in uncertainty of momentum, that is delta p, that will be nothing but 2p sin theta. Now p can be written as h upon lambda, so you can write this as 2h by lambda into sin theta delta p. So this is your momentum uncertainty. Along x-axis you can say this is delta px. Okay, now how can you minimize this momentum? So if you decrease the wavelength, you can see, and if the theta is increasing, if lambda is increasing and theta is decreasing, then your delta px will be decreasing. That means delta px will be minimized only by using this half angle is large and this lambda is less, lambda is high. That means the energy of photon is less. But if you want to do this, you have to compromise with position, with uncertainty of position. So how this is happening? Let us tell you. So when this electron is going to this eye, so I cannot detect this electron as a localized particle. So what we will see? We will see the diffraction pattern, the wave behavior of electron, and for that diffraction pattern you will get the diffraction maximum, something like this. And if this is delta x, then you know from the diffraction maxima, first order diffraction maxima, that is delta x sin theta must be equal to lambda. So what will be happening in this case? So our delta x will be lambda upon sin theta. So this is your position uncertainty, lambda upon sin theta. Now if you see this two expression, if you increase lambda here, so here lambda will be increased also, and if you decrease theta here, so theta will be decreased here also. So you can see your delta px will be decreasing, but your delta x will be increasing, and the reverse will also be happen. If you decrease lambda here, so the lambda will decrease here also, so delta px will increase. So if you want to minimize one, either delta x or delta px, then other will be maximized. So if you want to measure position or momentum separately, there is no problem. But if you want to measure simultaneously, then the problem will be arised. So if you want to minimize other one, the measurement of uncertainty of one, then you have to pay the cost for other. So this is actually the uncertainty principle. This is the Heisenberg's uncertainty principle, and this is why we have to go to a new kinds of mechanics for microscopic particle, and that will be the quantum mechanics, obviously. So we will start from the next class, the Schrodinger equation. With the help of Schrodinger equation, how you can handle the situations of quantum systems by using Schrodinger equation. Why we have to replace the Newton's second law by using the Schrodinger wave equation. And before that, we need to some mathematical digression also, because everything that will be happening in Hilbert space, the mathematical model that is used for quantum mechanics is Hilbert space. So we need some mathematical digression. So we will discuss 2 or 3 class on this mathematical discussion, that is actually the vector space, linear vector space. So you need to some concept about linear vector space to discuss more detail about the quantum mechanics or the Schrodinger equation. Okay, so from the very next class we will start with some mathematical digression. Okay, thank you. So if you are new in this channel and if you enjoy the class, so please subscribe my channel. Okay, so the more video will be coming here. Okay.